Okay, so when we talk about average atomic mass, we're talking about the mass of the protons and the neutrons in the nucleus of an atom. Why don't electrons count for the mass of an atom? They're so tiny, right? They are so tiny. So they're so tiny, they are insignificant in terms of their mass in comparison to protons and neutrons. And so when we're talking about the atomic mass of atoms and of elements, most of our things exist as a mixture of a lot of different types of those atoms called isotopes. Have you heard that word before?
Yes.
What are isotopes? They are... They have different numbers of neutrons, right? They are atoms of the same element that have different numbers of neutrons. Okay?
Does that mean they have...
Oh, you got it. I'm sorry. I thought you were looking like you needed it. Okay.
No.
I'm good. All right.
That means they have different atomic masses?
They have different atomic masses because they have different numbers of neutrons. So elements occur as a mixture of isotopes, which just means they are atoms of the same element that have different masses, okay? Average atomic mass takes into account basically how many of each isotope there are. It's essentially a weighted average. It's a weighted average. And that weighted average is what gets reported on the periodic table. Okay, and we talked about this a little bit.
Yeah.
Yes, a little bit, maybe. Okay, the weighted average is what goes on the periodic table. So again, if I was going to ask you what's the more abundant isotope between magnesium 24, magnesium 25, I think this was the question on your test, it would be 24 because it's closer to 24, right? The average atomic mass is closer to 24. All right, we can use this equation here. Have we talked about the equation for calculating average atomic mass? Okay, this equation for calculating average atomic mass is essentially just calculating a weighted average. It would be like trying to calculate a weighted grade, right? If 90% of your grade is made up of this content and 10% of your grade is made up of this content, you'd calculate it the same way. So we're going to take the percentage of our isotope, like let's say if I pull a sample of magnesium and 1,000 atom sample, maybe 62% of it has a mass of 24, right? And so we take that percentage, and we convert it to a decimal, and we multiply it by the mass of that isotope. We do that over and over for as many isotopes as there are of that particular atom. All right, and then we add those all together, and that gives us our average atomic mass. So essentially, we're just calculating a weighted average. Okay?
And are chemists constantly doing this for every occurring isotope?
It's pretty much settled by now, right? It's pretty much settled what the averages are by now. So no, not a whole lot. Okay, let's go ahead and try a practice calculation with this just so we feel comfortable plugging that in. I gave you an example for the average atomic mass of copper. It says that there's an isotope that is 69.17% abundant and it has a mass of 63 AMU. Another isotope is 30.83% abundant and has a mass of 65 AMU. What's AMU stand for? Atomic mass unit. Okay, very good. So, it's just an and sign with that font. Okay, the first thing I'm going to do is here's my first isotope and here's my second. I'm going to convert that percentage to a decimal. How do I do that?
Move the decimal up 2 places.
Yeah, 0.6917 times 63. And then I'm going to add that to my second isotope, 0.3083 times 65. And I'm going to go ahead and add those together. So I want you to run that calculation and see what we get. Okay, so you need your calculator. Go ahead and run that calculation and see what we get.
Ooh.
Hefty.
Would it be 0.65?
Nope, the masses don't get changed, just the percentages get changed. Okay, so the 63 and the 65, they stay, because those are the masses. The percentages are the only thing that gets changed to a decimal.
Right next to zinc.
So I got about 63.6 AMU.
Whoa, I got the same thing.
Okay.
Wow.
is it so small?
How'd you get that?
Which one's so small?
Just do it. See
Well-
oh, we don't
Try
have
this one on your own. Be careful with your percentages here. Are we better?
Yeah.
Good with that? Okay,
So it's the percents you're moving to decimals?
that's right. You don't move the atomic masses, just the percentages.
Okay. After I added them together, I got the right answer.
Very good. All right, now that we've talked about atomic mass, we're going to move now into kind of a parallel, which is called molar mass. Have you studied molar mass before, or is that new?
I've heard the term.
Heard the term.
From you.
Everything that we said about moles, we've heard before, or no?
Everything that you said about moles earlier made me dislike that.
No, moles are good. All right, so molar mass. The term molar mass and the calculation for molar mass is the mass of 1 mole of a pure substance. That pure substance can be either elements or compounds. Now, let's review here. What is a mole?
It's an animal.
No. Besides that, what is a mole?
It's a thing on your face.
Okay, that's close-ish. Okay, a mole is similar to a dozen. Remember we talked about this? It's similar to a dozen, but it's a lot bigger. So a mole of anything is 6.022 times 10 to the 23rd of anything.
That is large.
It's a big number, right? It's a big number. So when we say a dozen, how many is a dozen? 12. And does it matter what I'm talking about when I say it's a dozen? No, 12 roses is also a dozen baseballs, right? A dozen is a dozen is a dozen, no matter what you're talking about. The same is true for a mole. A mole is 6.022 times 10 to the 23rd of anything. Now, most of the time we apply that to atoms or to molecules, right? Because this number, this quantity of things, if you had this many oxygen atoms, that would mean you have 1 mole of oxygen atoms. Right? And if I had this many carbon atoms, that would mean I have 1 mole of carbon atoms. The reason we give that term mole is it makes our numbers more manageable. Rather than have to do all of our calculations with these numbers of atoms, it gives us a more manageable measurement. So I could just say I've got 1.2 moles, rather than saying I've got 6.94 times 10 to the 24th atoms, right? That is bulky. A mole gives us a manageable number to talk about quantity. It's not about mass, it's about quantity. Okay, yes.
So it's like a mole.
Let's examine here the units. Let's examine the units for molar mass. Grams per mole. That's how we say that, grams per mole. And so what it says is that 12 grams of carbon is what 1 mole weighs. Right? 1 mole of carbon weighs 12 grams. Right? If we say it like that, 12 grams per 1 mole. Okay? That's how we use that. Now I will tell you, moving forward, we use molar mass almost exclusively. There's not a real need for us to talk about math on the atomic level, right? When we're talking about chemical reactions, we're not talking about single atoms. We're talking about grams of atoms. And so we're going to be dealing with molar mass almost exclusively, but you do need to know the difference between atomic mass and molar mass, especially with that unit.
It's funny how they abbreviated mole.
Missouri. I haven't seen moles
It could
yet.
be MLC, molecule.
Could be.
That's lame sauce.
I don't know. I've never seen it. All right. If we need to find the molar mass of a compound, we take into account the mass of all the atoms in that compound. So we got to count up all the atoms in that compound and take those into account. We add up all of those together. So if I have a compound here, can somebody name that compound for me? It is an acid. I would agree with that.
Sulfuric acid.
Sulfuric acid. There we go.
It was
Sulfuric
on
acid.
the test.
There you go. It came from sulfate, so it's got to be sulfuric acid. Very good. Now, let's figure out how do we calculate molar mass. Need your calculator, need your periodic table, okay? How many hydrogen atoms are present here? 2. Okay, so I'm just going to start adding some things up. I've got 2 hydrogen atoms. What's the molar mass of a single hydrogen atom? You find that directly on your periodic table. What is it? 1. Okay? Plus, how many sulfur atoms do we have? Just 1. And it has a molar mass of, go find sulfur, 32, right? And how many oxygen atoms do we have? We have 4 oxygen atoms. They each have a molar mass of 16. Now, tell me what questions we have about where these numbers came from. Right? This is for our hydrogens. This is for our sulfur. This is for our oxygens.
This is 16.
Oxygen has a molar mass of 15.99. We're going to round that to a whole number. Okay? Remember how we memorized those elements 1 through 20? So this would go faster, right? So you know those molar masses right away. Okay? All right, so then I just add them up. That's it. Okay, go ahead and run that number and see what you get.
You really just spoiled it. You actually just spoiled it. No, they call me
Units have to be grams per mole. Grams per mole for molar mass. Okay, grams per mole. Does that seem simple enough? Just adding them up, right? We're going to take into account all of the atoms present and add them up. Okay? All right, let's try.
The next one is something with phosphate.
Yeah, do you know what this one might be called?
Ammonium phosphate.
There you go, ammonium phosphate. Very good. NH4 is ammonium, and phosphate is PO4 minus 3. Very good. Okay, now let's examine what's happening here. What's this 3 relate to? What's it pertain to?
The charge of phosphate.
Okay, I'm sorry. What does it only account to hydrogen?
No.
It has to count for both. It has to get distributed through there. So when I say distributed, what's that mean? Added or multiplied? Multiplied. Okay, so how many nitrogens will I have?
3.
I will have 3, and they each have a mass of 14. How many hydrogens will I have? 12. 12. They each have a mass of 1. Phosphorus is next. How many phosphorus atoms do I have? I have just 1 phosphorus atom, right? Because it's by itself. And if there's nothing there, we assume there's a 1 there, right? And it is 31. Thank you. And then oxygen has how many?
16.
Okay, it weighs 16. There are 4 oxygen atoms present. Each have a mass of 16, right? The 4 right here pertains only to oxygen. It is phosphate. It's called ammonium phosphate, but we still just add up all of our things individually. The charge on phosphate makes no difference in mass, right? Because electrons don't affect the difference in mass. Let's see here. 14 times 3 plus 12 plus 31 plus 64.
149.
Okay. 149 grams per mole. I would agree with that.
There's one on
Because it's 3 times.
All right, now we're going to talk about something called percent composition. Percent composition. So what does composition mean? Makeup, right? It tells us we're trying to figure out what is the percent makeup of these different compounds. And so when we're talking about percent composition, we're not just talking about the number of atoms. We're not just saying like sodium chloride is 50% sodium, 50% chloride, because we're looking at the percent of our composition of our compounds by mass. So we're trying to find the percent by mass of different parts within our compound. Okay? Once we can calculate molar mass, then we can find percent composition, okay? What we're essentially doing is comparing the mass of the element on its own to the mass of the whole compound. It's like what you do when you find out what you got on a test, right? You take the part you got right, divided by the total, and that gives you your percentage, right? Well, we're doing that same thing with these compounds. We're trying to find out what's the percent of carbon in lithium carbonate, right? Or what's the percent of oxygen in beryllium hydroxide, or whatever it might be. So let's go ahead and start with this one here. Find the percent composition of C2H5OH. First thing we have to do here is find the molar mass. Find the molar mass. So I want you to try to do that. Did we get 46?
I did get 46.
Okay. So when it asks for percent composition, it means that we want to examine every element individually. Okay. It might ask for what's the percent oxygen in this compound, and then we're only having to compare oxygen to the total. But when it asks for percent composition, we're going to do all of them. We're going to tell the full composition of it. So the first thing I want to do is examine carbon's part of this. What is the mass of carbon within that 46? 24, right? Because there was 2 carbon atoms that each weighed 12, right? And so that's 24. So we're going to take the part of carbon divided by the whole, and that gives us, that gives me 52.2%. Right, I'm taking that times 100 after I do the math, right? I'm not going to write that part out, but to get that decimal to a percent, I'm multiplying that by 100. So that gives me, it tells me my compound is 52.2% carbon. To do hydrogen now, what's hydrogen's mass out of the whole?
6.
Yeah, we have to take into account all the hydrogen. So even though one is placed on the other side, we have to take into account all of that. So 6 of them in total that each weigh 1 tells me that hydrogen's part is 6 out of 46. And that would be 13.0%. I like to go with a tenths place here just to make our last step a little bit more clear, and I'll show you that here in just a second, okay? The last the last element we've got to look at is oxygen. What's oxygen's part out of the whole? Only 16, because there's only one of them. So 16 divided by 46 gives me 34.8% oxygen. Okay. So by mass, these are our percentages, right? 52% of this compound is made up of carbon. 13% of it is made up of hydrogen, and 34% of it is made up of oxygen. And so what's the way?
Carbon and oxygen with a bit of hydrogen?
Mm-hmm.
Okay.
By mass, right? By mass.
Yeah.
What's a way you can check your answers here? Add them up and see if they equal 100. They should equal really close to 100. You might be a decimal place off here or there, depending on where you rounded. That's why I encourage you to go to the tenths place. But that's a way you can check your answer. Now, I will warn you, if there's only 2 elements you're working with, you could just do the first one and then subtract from 100 to get your second one. But the problem is, if you do the first one wrong and you subtract it out of 100, now both of them are wrong. Okay, so I would recommend go ahead and do the math on both and then add them up to check your answer. All right. What's the percent composition of calcium nitrate? I want to go ahead and try this one, this last one here on your own, and then we're going to get started on the homework.